Dear students, we are going to discuss just this slide called profit maximization, because we need to link what we have learned about convex functions or strictly convex functions with something in economics. Assume that there is a firm which makes only one product and it fixes a price P for selling each unit of the product, maybe a piece of chocolate, right? Or a quantity of something, maybe ghee, maybe whatever, Coca-Cola, whatever. I'm not talking about what exactly the thing is. Now, when the price P greater than 0 is fixed, now once you make an amount X in the factory, then you sell it out in the market, then you get an amount of PX by selling it, and that's called the revenue of the company. Now, but companies sometimes are not always bothered about revenue maximization. Sometimes they are, but in many cases they are also bothered about profit maximization, which tells you, okay, what is the cost? If you subtract the cost of making the object, that X amount of stuff, then the remaining is your profit. So Px minus C of X, this quantity is called cost. Basic economics tells us that this cost function is usually considered to be convex. Now the question is why it should be convex, and of course you have to have x greater than or equal to 0. You cannot make negative amount of any quantity. So the problem that we are facing here is not an unconstrained optimization problem but a constrained optimization problem. You might ask, why should I really bother about your constrained optimization problem now? Let me tell you a trick that you have to remember all along your career as an economist. If you become an economist and you use mathematical tools like this kind of tools, optimization tools, that whenever your point of minimization or maximization is not in the boundary but in the interior, then treat it just like as if it is an unconstrained optimization and equate the gradient of the functions that you want to minimize or maximize to 0. That is the small key you always remember. Now you observe that for this problem, which is called the profit maximization problem, where we have subtracted from the revenue Px the cost. Now people would say, okay, okay, in economics books you know that usually cost is taken to be rather a strictly convex function, because you know that if I make 1 unit more of the cost, when 1 unit more of the object that I am manufacturing, then my cost would increase. That is a natural thing to assume, right? It may not also, but in general, most cases it will increase. So, which means that these cost functions have an increasing derivative, and as a result of which, you can easily claim them to be convex functions. We will show that it's possibly good to even take them as strictly convex function. Now, let us say we don't bother much about the convexity of Cx or anything else, just take it as an optimization problem. Only I know that the solution of this problem would lie in the interior of the region x greater than or equal to 0. That is the profit maximizing problem. If there is a one profit maximizing production level, that this is the level where the profit would get maximized, that production level has to be strictly greater than 0. It cannot be equal to 0. 0 means you have nothing. C0 will assume as 0. There's no, you have made nothing, so there's no cost. You have sold nothing, so there's no cost. So your profit is 0 when you make 0 amount of stuff. So x has to be strictly greater than 0, and hence is inside the set x greater than or equal to 0. So what you will do, suppose x naught is that, or x star for example is the profit maximizing production level, then you take the derivative of Px minus Cx, assuming that C is a nicely differentiable function, maybe twice continuously differentiable. So Px is equal to Cx means P, so the derivative of this is P minus C dash x, and that at x star must be 0 if x star is the minimizing point, because I told you once you are in the interior it behaves like an unconstrained stuff. So P is equal to C dash X star. So the price that you said is actually the derivative of the cost function at X star, or the marginal cost function evaluated at X star. Marginal cost function means the rate of change of the cost function at any given point X, which means nothing but the derivative of the cost function. Marginal change essentially means if I add 1 unit, how much would be the rate of change? If I add delta X unit, what would be the rate of change? So that's again as simple as that. So it's the rate of change of the cost function at every level of production. So that's the derivative. That's what you want to know. So the price is equal to C dash X star. It is the rate of change at the maximizing production level. Now, of course, if X star was the real minimizer, then you what would you do? You would actually check what is the second derivative. X star is the real maximizer. You have to show that the second derivative would be strictly less than 0. Then you will know that this is the maximizer, because I don't know anything about any additional thing. Suppose so the critical point satisfies P equal to C dash X star. Now if you want to show that X star is really the minimum maximizer, then you have to take the second derivative, which is minus C double dash X star, and that has taken to be strictly less than 0. If you want a cost function which will give you something like this, you really have to admit that minus C double dash X star is strictly less than 0, or C double dash X star is strictly greater than 0. So in a better way, it is always good to admit that I will take a cost function which is having C double dash X star, or the second derivative, strictly greater than 0. Later on, we will show that any function which has a second derivative strictly greater than 0, any function, differentiable function which has its second derivative strictly bigger than 0, any twice continuously differentiable function which has its second derivative strictly bigger than 0 is actually a strictly convex function. So this assumption that the cost function is strictly convex is not a bad assumption. So these things that you have learned, they come into very simple and very practical problems like profit maximization, which most of us would understand immediately. So with this, I would stop and go on very soon to talk about some properties of the convex set, and I'll show you that budget sets, if pricing is tweaked with a bit, may not always give you a convex set. So thank you very much.